Okay, so after we cover our introduction to the ionic model, we look at the covalent model. So covalent basically means together with valence electrons. And so this is the one where when they bond, the electrons end up being shared. So we're going to focus, when we think of covalent bonding, we're going to think of nonmetals doing this. And so noble gases are nonmetals that do not bond. They've got the full outer shell of electrons. They're stable as they are. And so with a few rare exceptions, noble gases basically do not bond. But pretty much every other nonmetal does bond. And when it does that with other nonmetals, including itself, it bonds covalently, so through sharing electron pairs. And so what we're going to focus on when we do covalent bonding is trying to give every element an octet, which means a full outer shell of electrons. So hydrogen's octet is not really 8 valence electrons, it's going to end up being 2 electrons because hydrogen only has a 1s level, so it can really only accommodate 2 electrons. But for other elements beyond hydrogen, other nonmetals, having 8 valence electrons gives it a noble gas configuration and makes it very stable. And so we're going to get that octet through a combination of shared electrons and unshared electrons. The shared electrons we call bonding pairs, and the other ones, the ones that aren't being shared, are called non-bonding pairs, or we'll often call them lone pairs. Okay, so the way that we draw these things are called Lewis dot structures. So let's start with the elements that are known as the diatomic elements. So there's 7 elements that the IB is going to expect you to know when you have them in their pure, most stable form, their standard state. They exist in these little 2-atom molecules, so they are called diatomic elements. Those elements are hydrogen. So when we have a hydrogen gas, it's not just H atoms, it's actually little H2 molecules. So hydrogen is kind of by itself on the periodic table, but then the other 6 are right next to each other. So they are N, O, F, Cl, Br, and I. And so when you have nitrogen gas, you don't just have N atoms, you have N2 molecules, O2 molecules, F2 molecules, and so on. So these are the diatomic elements. This is a sort of cartoon image of what a hydrogen molecule would look like, or an oxygen molecule. There's a couple other elements that are kind of interesting and that they sometimes bring up, which is phosphorus and sulfur. Their actual standard state is P4 and S8. So those are kind of cool. Sulfur actually forms a ring with itself in its most normal state. Okay, so let's try to draw these as Lewis structures. So for hydrogen, hydrogen has 1 valence electron. So we represent electrons with dots. And so the other hydrogen has a dot. And so we kind of go into this knowing that the formula is H2. So I want to show those hydrogens sharing the electron pair. So one way to do that is to just draw the dots, the pair of dots between them. And that implies that that pair between them is being shared. So that's fine. You could also do it like this, with a dot and a cross, to imply that 1 electron came from each. Or really the simplest way is just to draw a line between them. And so that line represents a covalent bond. It represents a shared electron pair. So again, now we're figuring out how to get octets. So if I think of a simple one like F and all the other ones that are in group 17 have 7 valence electrons. They only need 1 more, and so they're only going to form 1 bond. And so if you get 2 Fs together, then they both have 7, and therefore they're going to share this pair. So if I were drawing this, I would just quickly draw a little line segment between the Fs, and I would get my little F2 molecule. Cl2, Br2, and I2 are going to look exactly the same because they all have 7 valence electrons. Oxygen's a little bit different. So oxygen has 6, and therefore we can tell it needs 2 more, and it will achieve that through bonding. So it needs to form 2 covalent bonds. So you got O. I'm going to draw a double bond with the other O. I knew that both O's would want to make, would need to make 2 bonds in order to feel like they have an octet. So in this one, we can see that each oxygen has 4 unshared electrons, and then these 2 line segments here represent 4 shared electrons. So we've got 4 bonding electrons, and we've got 4 unshared non-bonding electrons. Okay, and the other one also has 4 unshared non-bonding electrons. And so together that gives it the octet. Okay, so we can have single, double, and actually triple bonds. If I do N over here, N has 5 valence electrons, and so I can tell it needs 3 more. So if I have 2 N's together that both need 3 more, then they're going to share 3 pairs of electrons. But that's kind of sloppy, so we rewrite it as line, 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 pair, pair. So there's all these ones are the bonded electrons. There's 6 bonded electrons there, shared electrons, and then there's 2 electrons being unshared. So together that's the octet. Phosphorus and sulfur, I wouldn't expect anyone to be able to come up with on their own. Phosphorus actually forms this kind of cool pyramid where each phosphorus is bonded to, let's see if I can actually figure out how to draw this, 3 other phosphorus atoms in kind of like a trigonal pyramid. Did I do this right? No, I don't think I did. Let's see. They should each form 3 bonds. What am I missing? This one's not forming 3. What did I do wrong? No, it is 1, 2, 3. Okay, yeah. So it's really sloppy. It's hard to draw on the page because it's got 3 dimensions. But actually, each phosphorus is kind of in a little triangular pyramid, if you will. And so that's how you draw it. You wouldn't really be expected to draw that one generally. And then the sulfur is just a ring. So sulfur has 6 valence electrons. And so you're going to expect it to form 2 covalent bonds to fill out its octet. And so if each sulfur forms 2, 1 out of each side, we can get this ring of sulfur atoms where there ends up being 8 total. If I squeeze another one in here, and they would each have 2 lone pairs to fill out their octets. So that's actually how sulfur, the element, is bonded. Okay, there's some more practice here. Again, they're kind of all just like a puzzle. So when you got H2O, you've got H, and you've got H, and you've got O. And you need to kind of figure out how many more electrons does each element need to have its full shell. H just needs 1 more, and O needs 2 more. So in combination, if O shares 1 with each H, then you can get a full outer shell for all the elements, and you can get a Lewis structure like this. It doesn't matter if you draw it like that, straight, or bent like I did. They're both accepted in terms of Lewis structures.